Ladies and gentlemen, good afternoon, everyone. So we are ready to start the second lecture for this short course on seismic isolation. First of all, I want to start by asking if there is any question about what we have discussed yesterday from anyone. Okay, good. Anyway, if you will have any other questions, feel free to interrupt me whenever you want. So today, our lecture will focus on the standard code on experimental tests for anti-seismic devices. The European standard code, which is the standard EN 15129, the version of 2009, is actually a standard code which is very important for anti-seismic devices, generally isolation devices, because in that standard, there are all the experimental tests for all the typologies of devices which are listed and described. Actually, there is the procedure which is described, so the all the parameters that have to be set according to the used testing equipment, and also the requirements, the final requirements that have to be checked by the data processing procedures. And the data processing is actually what we are going to do tomorrow afternoon in the numerical laboratory. So I will provide you to some experimental data for full-scale devices, actually real data which have been returned by experimental tests for some activities in U Center Foundation, which has actually one of the largest worldwide testing equipment for anti-seismic devices, which is the bearing tester system. We will have the occasion in this lecture to describe the performance of such equipment. And we will be able to analyze all the outcomes, the main outcomes of such tests in order to come up with the main mechanical properties for all the typologies of isolation devices. And actually, we will do that by using the MATLAB environment. So this was the reason why I asked in the first inquiry to rate actually your programming skills. We will use extremely basic instructions for the MATLAB programming skills. So this means that you don't have to worry about anything, because I will do together with you exactly the same procedures. The only issue that we have to ensure is if you have your own software installed in your laptop. I mean, you have MATLAB already installed in your computers, rather than you need MATLAB. There is no problem, because I can provide you not the software, unfortunately, but I can provide you to a remote desktop connection to some computers that we have at the Faculty of Engineering, Civil Engineering here at the University of Pavia. And in those computers, there is also MATLAB environment installed. And there is, for next week, also installed the software SAP 2000. And it will be also an ultimate license only for academic purposes. So it cannot be used for commercial activities, but just for academics. So in order to know if you did actually this connection, I kindly ask you to send me an email within today by saying that you need actually the connection, the remote desktop connection to access actually the computers here at the University of Pavia in order to use MATLAB, because you don't have the program already installed in your computers. The software for the connection is remote desktop for Windows, and I know that if any one of you has Macintosh, there is no problem, because I think that there is also remote desktop as an application, extra application for also for Macintosh. So there is no problem. Just highlight that in the email that you will send, so that I know that you need some instructions, some additional information for the execution of the remote desktop link. Okay. Is there any question about this organization for tomorrow? It will be just a file. I will send the file by answering to your email, and you will have just to add a password to the connection link, and then everything is done. The only thing that is that you will have to run both the sharing of that desktop together with the connection through Zoom, because you have to see what I do, and then try to do it also in your computer. There is no problem, because it is actually a frame, a window, which can be moved in your screen, so it is exactly very similar to what we do actually with Zoom and other softwares. So don't worry, we do everything very smoothly, because we have all the tools to allow everyone to use exactly the same software, the same computations, and so on. Okay, so the same for this week and next week. Next week we will deal with SAP 2000, and we have, I think that maybe you will need, all of you need the license, so there is no problem to use exactly the connection of University of Pavia. Okay, so if there is no question, we can start with the presentation of today. I share my screen. Okay.
I'm sorry, Professor. This
yes.
is Catareggia.
Yeah.
I have a question on the lecture of yesterday.
Yes.
If you could say a bit more about the design of the seismic isolation when we deal with a flexible structure, and maybe on a soft soil. I mean, what do you suggest in these cases, how we should preliminary design, let's say, the isolators? Thank you.
Okay, I see your point. Actually, for design rules, there will be a lecture entirely dedicated to these issues, and I think it will be on this Friday, where I will show some very fast rules to get started design, an initial design for devices. But what you were mentioning can be referred also to the lecture of yesterday, so an introduction of base isolation. So your question is actually when we have an already flexible structure rather than a soft soil, so that the structure soil structure interaction leads to a higher value of period. Can we use base isolation, or how can we design the bearings? So how to design? I just switched to the question to the lecture of Friday, so that we will see actually all the rules for the definition of all the technologies, which are actually rubber bearings, lead rubber bearings, and friction pendulum. But concerning the implications of the flexibility of this of the building rather than the structural system, rather than soft soil, we can say that there is a very important parameter that we discussed about yesterday, which is the minimum period for designing isolation systems. And this is very important because if the structure is already very flexible, so the stiffness is very low because maybe it is a high-rise building, or there is actually the soil structure interaction with the soft soil, maybe there is no need for base isolation, for seismic isolation, maybe, but this can be assessed directly through the computation of the minimum value of a period to design isolation systems. Anyway, we can always find and assume a numerical value for the design period higher than the minimum one which can be returned by our computations. What we have to check is that this assumed initial value for the design value of period then returns, according to the procedure that you will see on Friday, returns some designing of devices which are actually which can be done actually in real practice. So with the sizes and mechanical properties which make sense in real applications and also in practical applications. So maybe you come up with numbers because generally, this is a general rule, procedures just lead to numbers. And then as engineers and as the researchers and practitioners, we need to understand these numbers if they make sense or not. So maybe we get to a producer with some characteristics of our bearings, which have been designed with a single value of isolation period, and maybe the producer just says that it does not make any sense because the sizes or the mechanical properties don't fit with the realistic behavior of real devices or full-scale devices. And there is also another issue. Maybe if we deal with the high-rise building, there is another issue, which is the overturning effect. Because maybe if the building is very high and very small, is very thin, let's say, maybe we have a very large effect of overturning moment, so that we may have some tension in some bearings. There is a little bit of amount of tension for rubber bearings, but there is no tensile strength, let's say, for sliding devices, for instance. So this means that you start having uplift. And once you have uplift, you have also impact forces when the overall structural system goes back. So this is another issue. When we have obviously soft soil, that is another issue because we have the soil structure interaction. So the elongation of period just due to the characteristics of the soils, and so the again, I think that the minimum, the very meaningful parameter is the minimum value of period, which is very important because it automatically says that how can be designed your devices, and then once you get, according to the design procedures, the sizes and the mechanical properties, you can decide if the final result, the numerical final result, makes sense or not. I don't know if the question has been answered completely.
Yes. Thank you for
perfect. Yeah, it is a very good question because generally that is very key issue when designing base isolation systems. Let's say generally seismic isolation, because maybe we are considering a structure which is already very flexible. So as the flexibility increases or the stiffness decreases, we know that automatically we have a sort of period elongation, but just due to the flexural behavior of the building itself. And so maybe we don't need any isolation system, but this can be checked, obviously. And we always have to check also the main cause of the flexibility of the structural system. Because maybe if it is a high-rise building, what I mentioned, the uplift rather than the tensile forces in the bearings, rather than soil structure interaction, okay, maybe we can also provide some base isolation. So any other questions? Okay, so I will provide you also both the on Friday there will be I will deliver a presentation specifically on fast design rules, but I will also provide a paper, a research article I have authored on the topic, and actually I will explain just the fast design rules that I will deliver within the presentation. So starting with the lecture of today. As I mentioned, the lecture will deal with the European standard code for anti-seismic devices. This is the standard code, the EN 15129. You see it was issued on November 2009. And it is actually the a European standard for testing and generally with all the requirements for isolation bearings. There are a number of them. Actually, this is a very large standard code because it does not contain just isolation bearings, but also dissipating devices. So something like dampers, STU, shock transmission units. So it is a very wide standard code with a number of devices which are ruled. Let's say generally anti-seismic devices. So dampers are just devices which provide just energy dissipation. They are just like jacks. So the actually truss elements with particular behaviors because there is oil in a chamber which provides actually viscous forces, and so automatically we have damping and energy dissipation. But actually now we will focus just on isolation devices. And in table 1 for this standard code, we have the most common types of anti-seismic devices. Here I just report the seismic isolators. But you have to know that in this standard code, as I mentioned, that there are also other typologies of devices, some typologies of displacement based devices, velocity based devices, rather than dampers, STU, and so on. So what we have seen yesterday is actually represented here. So all the isolators which have been considered by the European Standard Code are actually the same that we have discussed. You can see the elastomeric bearings, which are divided into elastomeric, purely elastomeric, so rubber bearings, and lead rubber bearings. But as you can see, both of them are related to the same paragraph of the standard code. So this means that both the typology of the anti-seismic devices, so the rubber bearings and the lead rubber bearings, will have exactly the same testing protocol in real applications. So we have exactly the same tests to be performed, and we have just to look at the different quantities when we have to do data processing of the return signals by the testing equipment. So you see also the some drawings and some symbols that are used within the standard code. And you notice that for the lead rubber bearings, there is something which seems a hole, but it is actually the lead core, which provides the high dissipative behavior of such bearings. Then we have curved surface sliders, which are actually friction pendulum devices. They are related to the paragraph 8.3. We will see all the main tests and all the main requirements. You see there are two arrows, double arrows, which suggest that actually it is a bidirectional device. So all the plane horizontal motions can be bidirectional actually. And we notice that it is curved surface slider because also there is this symbol, so the curved surface for the isolation bearing. Yesterday we have seen that we can have just a single sliding surface rather than double with a non-articulated slider rather than an articulated slider with a hinge. And then we have multi-stage devices, so with multiple sliding surfaces. But generally in this standard, they are just represented as in this way. Then we have one device that we have not considered yesterday, but it is actually one of the simplest. And this is the flat surface slider. So the flat surface slider is exactly a sliding devices, but with a flat sliding surface. So it is exactly a plane. It is a bidirectional one. There is actually this paragraph 8.4. And okay, this is listed as a seismic isolator, but generally it is not considered properly, I mean, as a seismic isolation device, because actually the flats, I mean, we have seen yesterday the main goals of isolation devices. One of them, actually the last which was listed, is the recentering capability, so of the device. So something within the device which provides a response, a force response, which leads the structure towards the zero displacement configuration. And actually, for the flat slider, we don't have anything of that. We can maybe have something coming from the elastic behavior of the superstructure, as we mentioned yesterday, but there is no response, no force response provided by the device itself. I mean, due to the recentering behavior. And this is actually what happens when we try to push any kind of objects. If we take our laptop, we push it, and then we remove the load, the laptop stays exactly in the same place where it has reached. And this is exactly what I meant. What I mean. There is no behavior, recentering behavior for just pure friction. And if we move our laptop on the desk, this is exactly a flat slider, because we are making the laptop sliding toward a flat, a completely flat surface. So this is the reason why the flat sliders are actually not seismic isolators, just because there is no recentering behavior. But actually, they are listed and described within this standard code, just because they can be used in hybrid systems. So together with other isolation devices. And this is actually what happens with the elastomeric bearings. So with the rubber bearings, both the rubber bearings, purely rubber bearings, and rubber bearings with the lead core, so lead rubber bearings. Because we will see on Friday, according to the design procedure, generally, what we get in design is that, remember that all the isolation devices must be at the beginning just structural bearings. So they have to carry vertical loads, so gravity loads. Maybe we have, given a structure, we have a certain number of structural bearings. Okay, so we need those points to provide vertical reaction against gravity loads. Okay.
So can I ask you? So
yeah.
The problem of flat surface sliders is that they rely purely on friction with their mechanism. That's why they are not useful as seismic devices, because we don't have recentering.
Yeah, exactly.
Okay.
Yes.
Yeah. Perfect.
Yes. And also because of the purely frictional response, you see, you know that the hysteretic behavior for the purely frictional response is just a rectangular hysteretic rule. So this means that the residual displacements that we could have is exactly the maximum one. Okay, so because when we reach the maximum displacements and then we go back to zero force, it is exactly the point with the same displacement as the maximum one. So this is actually the problem related to the absence of any recentering capabilities of the device. But they can be used, obviously, together. I mean, together with elastomeric bearings, because we will see that in real applications, it is quite uncommon to find a number of elastomeric bearings, which is actually equal to the number of structural bearings for a given building, rather than bridge generally structural systems. So this means that we have maybe we have 25 structural bearings points, and then we get maybe 10 rubber bearings according to our design procedures. So this means that we need 10 rubber bearings of certain sizes with some mechanical properties to have exactly that period with that damping and actually to provide that was a particular a certain value of stiffness, of lateral stiffness. So in order to have our performance point, we will call it performance point. But then I know that I have just 10 isolators, but I have to cover actually 25 bearings. So I need some other devices, and those devices will be actually flat sliders. And actually the flat sliders, in order to not to mismatch the initial results of design, will have actually a very low friction coefficient. If we can decrease a lot the friction coefficient, the force response will be very low, so that the overall lateral behavior of the structural system will be associated to the 10 isolators, and automatically we are not changing what we have guessed at the beginning of our design procedure. So this is the main aspect that we have to pay attention on when we have to use hybrid systems. So this means rubber bearings with or without lead core, together with flat sliders. And flat sliders are also used with unlubricated, non-lubricated materials, but those are actually other applications. So for what we will consider just flat slider with lubricated materials. So this means that the friction coefficient will be very low. So at least maximum 1% or even lower. And so this is not what happens, for instance, for curved surface sliders. For curved surface slider, we will provide exactly the same isolator for every bearing support point. Okay, so we will have just curved surface sliders. But for elastomeric bearings, according to the mechanical properties which are returned by design procedures, it is quite uncommon to find an isolation system based just on rubber bearings, but we need hybrid systems, so together with flat sliders. Actually, it is not possible to use hybrid systems with curved surface sliders because, I mean, curved surface slider and flat sliders, just because, first of all, generally, those kind of devices, these kind of devices can lead to the proper design definition with actually the same bearing everywhere. But actually there is also a compatibility issue due to the vertical motion, because curved surface sliders leads to the pendulum motion, as we have seen yesterday. So there is a vertical motion provided by the spherical shape of the sliding surfaces, whereas flat sliders are actually with the zero, provide motion with the zero vertical displacement. So you will induce, if you use both of them in the same structural system, you will induce some extra internal forces due to the compatibility, so the changing differential displacements at some points. So you are inducing, maybe if you have a reinforced concrete plate, you are inducing differential displacements, and so automatically bending moments, and they could be very large, because curved surface slider devices can move upward and downward of few centimeters, but if you compare a few centimeters with the zero displacement, you have a relative deformation which is very high, and which could cause actually very large internal forces. So there will not be any hybrid system related to curved surface sliders, but we can have, and we will actually have, depending on the performance point initially assumed, hybrid systems with the rubber bearings, with and without the lead core. So about the experimental tests, there will be horizontal and vertical tests. According to the horizontal tests, they are basically performed by considering displacement control. So this means that the testing equipment just applies the time series of displacement to the device, and actually starts to record the force time series which is needed to provide that displacement. Okay, so these are the main results of the testing equipment, together by keeping the vertical load as a constant value during the whole duration of the horizontal motion. There are vertical tests where the vertical load varies for a given waveform, and generally it is a trapezoidal waveform, but with no motion, with no horizontal motion. Actually, it is just a compressive test, and no motion is applied. But for horizontal motion, we achieve the vertical load very smoothly with a ramp time series, and then it is kept constant during the whole duration of the test. And yeah, the main goal actually is to keep it constant. But what we actually find out at the end of a test is that the testing equipment tries to keep it constant, but maybe there is some fluctuations, especially for friction pendulum bearings, because in friction pendulum we have also the vertical movement induced by the spherical surface. So this means that the actuators which are installed within the testing equipment try to keep the load constant, but they have also to follow the vertical deformation of the bearings. So the overall behavior is actually to provide also additional fluctuations, but they could be very low. And then, as I mentioned, the force which is needed to displace the device according to the input signal of displacement is continuously recorded, and then this will provide the force displacement response, which can provide actually all the mechanical properties of the bearing by considering the data processing procedures that we will see. So let's start with the first typology ruled by the standard code. So the rubber bearings, elastomeric bearings, and with elastomeric bearings, I mean low damping rubber bearings, high damping rubber bearings, and also lead rubber bearings. So also the rubber bearings with the lead core. So you see there are some, I just provided in this presentation some of the most important paragraphs of the standard code, and you see there is just there are also definitions for high damping and low damping. Actually, the standard code defines the high damping rubber bearings if we have a damping ratio higher than 6%. Generally, at 100%, you see XCB means at 100% means at 100% of lateral shear strain, which is actually what we mentioned yesterday. I just throw it here just to remind. It is actually the ratio between the applied displacement and the height of the rubber bearing. So this is the displacement, this is the height, the shear strain, lateral shear strain is actually equal to the displacement over the height. Specifically, the height should be the height, just the summation of all the thickness, all the thicknesses of rubber layers, and also without the steel stiffening sheets. But actually, it is quite similar to their values are very similar. So the standard code says that we have high damping if we have damping ratios higher than 6%, but also generally also 10% damping can be considered as low damping. And we have low damping if the damping coefficient, the damping ratio is lower than 6%. And there are also other definitions. We had obviously the lead rubber bearings, high damping and low damping, but we have also polymer plugged rubber bearings, which are actually particular and specific devices with the polymeric, high polymeric material, high damping polymeric material, which is something like an addition like the lead core, which provides a higher dissipative capacity to the device. So now we start by analyzing all the tests which have to be performed on the devices. I don't want to read obviously all the paragraphs, but I want you to have them in order to clearly understand what is ruled by the standard code. I will just highlight the most important issues, and these are in this paragraph. These are actually the tests related to the dependence of horizontal characteristics on the rubber shear strain. So this means that according to this test, this is a set of tests, we are trying to investigating the variation, the possible variation of the mechanical properties of the devices if we change the maximum lateral displacement. So what this means is that we fix the vertical load we fix also the frequency of the motion, which is directly related to the maximum velocity. And then we vary the maximum displacement. And we vary the maximum displacement according to these values. Plus and minus 5%, 10%, 20%, 50%, and 100% under test condition using procedures given exactly, and so on. So this means that these are shear strains, exactly like the 100 that we consider in the previous slide. So this means that we have 100 actually, which is the key reference, the maximum reference for the testing protocol. But we consider increasing values of shear strain. And generally, what we can find is that if we consider higher and higher displacements, we get actually a decreasing value of damping, and we get also a decreasing value of shear modulus. That should be the general behavior that can be observed in the experimental tests. And this is actually what we want to analyze by considering the data processing of those tests. We just consider same frequency, same vertical load, but we vary the actually the maximum displacement, and then we compute for all of them the mechanical properties according to the force displacement loop. And then obviously we can do some reasoning about the dependence of such characteristics on the maximum shear strain. So what we can observe is actually, you see, everything is listed here. So the horizontal characteristics can be the effective horizontal stiffness, KB, and the equivalent damping factor, the equivalent viscous damping. And the stiffness, the equivalent stiffness, is actually the stiffness computed at maximum displacement, the secant stiffness at maximum displacement. And the equivalent damping ratio is actually the damping ratio, which can be computed according to the hysteresis area, as we have mentioned yesterday, according to the Jacobsen formulation. We tried to we have computed actually the expression for the equivalent viscous damping for given a general hysteretic behavior, and actually it is something like that. The equivalent viscous damping is equal to the EDC, energy dissipated per cycle, so the hysteresis area, divided by 2 pi's maximum displacement and maximum force. Okay, this is the Jacobsen formulation. We have seen how to derive this formulation. And EDC, this is very important. EDC shall be computed according to a single cycle. So this means that generally these are tests. Maybe I didn't mention this, but it is very important. All the horizontal tests are performed under displacement control, but the displacement signal, the input signal, is an harmonic signal, and it is actually something like this. Generally, we have time and displacement, and we have something like this. But then we could have also multiple cycles. Okay, I think that we will have 3 or 5 cycles. Then there will be a specific test, repeated cycles, and that we will see later on in the slides, which is actually 10 cycles of harmonic motion. So this means that the EDC, the hysteresis area, has to be computed for just a single cycle. So for this, and then this automatically implies that you can compute EDC for all the cycles which have been applied to the device. And this is another issue which can be considered in the data processing, which is actually the dependence of the mechanical properties on the cyclic excitations. So as the cycles goes by during the motion, how to model and actually how to see if the characteristics of the bearing varies or not. So this is another issue that we will check tomorrow in the numerical laboratory. We will have to find out a very easy way to detect immediately the cycles for a given signal, and then we will see how to compute the energy dissipated per cycle, the damping. We will see how to consider the degradation of mechanical properties due to the multicyclic excitations, and so on, something like that. Generally, this is not actually the starting point for a testing equipment, because as you know, this is the time series of displacement, and it starts with the slope, which is different than 0. And the slope of a displacement time series is actually the velocity. So if we start with a slope different than 0, this means that this time series of displacement starts with an initial velocity which is different than 0. So actually, we cannot start in reality with a gap of velocity, because there is no gap in reality, as someone has mentioned before. So this means that we need some sort of starting loop, something like this, okay, which is not actually accounted as a loop, as a fully as a cycle, but it is something which allows the testing equipment to have exactly that value of velocity and 0 displacement at the starting point of this input of the input signal, and at the same time we have an ending loop. Okay, but finally in the data processing we will have to consider just 2 cycles in this figure, and then so we have cycle 1 in this figure and cycle 2, by neglecting all the computations for the starting and the ending loops. Okay, so we will have to compute all these characteristics for all the loops, so that we can compute also the dependence of such characteristics on the multicyclic excitations. Then, since this paragraph also rules the characteristics for lead rubber bearings, so the rubber bearings with the lead core. Yeah, I just finished this aspect, and then I will answer the question. Just a second, because it is important. And now I was mentioning the effective stiffness and the damping, but this is for generally rubber bearings. But then if we have lead rubber bearings or also the other typology of the devices with the high dissipative polymer, we have to characterize the post-yield stiffness instead of the effective stiffness and the characteristic strength, which is the force at which the force displacement loop intersects the vertical force. Okay. Yes. So please, the questions.
Yes, I just wanted to ask, Doctor, the equivalent damping here in the formula is based on the max, but this is only for testing scenario, isn't it? Not for design, I mean.
Yeah, well,
design
we will use exactly the same expression also in design, and it is quite hard to understand because actually this definition of damping is related to a fully reversed cycle, so something like this. So the maximum displacement is achieved at both positive and negative directions. But actually, what has been observed is that if we assume this behavior, so a fully reversed cycle, also in design, what we find is that we have exactly the same agreement between maybe a nonlinear time history analysis and easy design rules with just the Jacobsen formulation. So we use it to characterize full-scale devices in the experimental field, but we will use also in design. On Friday, you will see how to use this particular formulation also for design.
Thank you.
Yeah, you're welcome. Yeah, and actually, this was actually the final scope of my research article. My last research article tried to use very simple equations to design the seismic devices, and actually, I found in all the research activities that we have carried out here in Pavia, that this expression, even though there are strong assumptions, I mean, the fully reversed cycle, just one cycle, just one harmonic cycle, but it returns actually very good results as if they are compared, for instance, with the average results of a set of nonlinear time history analysis rather than also experimental simulations with the hybrid technique. And so this paragraph for this typology of tests describes the mechanical properties which are the most important for rubber bearings generally. For high damping and low damping, we have to focus on effective horizontal stiffness and equivalent damping factor. But for lead rubber bearings, we will focus on the post-yield stiffness and the characteristic strength. This is for testing. I will add also another parameter for design, because also for lead rubber bearings, the effective horizontal stiffness is very important, because it is directly related to the design period, which is assumed at the beginning. In tests, these are the main parameters which are considered for the final requirements of the standard code. But for design, we have also to consider the second stiffness, so the effective horizontal stiffness. Then these are the requirements for these typologies of tests. So the value of the key parameters, let's say KB and the damping ratio for rubber bearings, rather than the post-yield stiffness and the strength for the lead rubber bearings of the third cycle are reported for the rubber shear strain tested. So you see that for this standard, the mechanical properties of the third cycle are very important and are under investigation, because maybe the standard code assumes that the very first cycles, the very first two cycles allows the device to achieve a stable response. So as you see, then there are also the definition. If the design rubber shear strain is not included in the test strain listed, then there will be linear interpolation with respect to the values that we have. okay, generally 100% of shear strain is what is assumed in design, but there could be also some difference in some design application. So there could be also the possibility of linear interpolation. And the test frequency and the reference frequency has to be reported, obviously, within the the testing protocol. The testing protocol, you will see that consider 0.5 Hertz as the frequency, rather than the isolation frequency, which is defined by the structural engineer. And this is a sentence which occurs many times in the standard code. There are values which are approximately fixed unless the structural engineer provides justifications for other values related to the application. And then you see one of the most important requirements is related to the mechanical properties for rubber bearings, effective stiffness and damping ratio, rather than positive stiffness and strength for lead rubber bearings. For the third cycles, at the design rubber shear strain shall both be within plus and minus 20% of the design value. So this is a check, a quality check for the device. We have a target value which is defined according to the design, according to the numerical simulation that we have carried out before. Then we go to test devices, and the experimental values should fall within a range of plus and minus 20% of the target values. Whereas the value KB, so the effective stiffness at 5% shear strain, which is, I think it was the very first value, yes. Or the strength for lead rubber bearings should be sufficient to provide adequate restraint as determined by the structural engineer against wind loading. Obviously, we have to keep in mind that we are designing anti-seismic devices, but at the same time, there will be also other typology of horizontal loading, such as wind loading. So there will be the overall isolation system should be flexible enough to provide the period shift, but it should not be too much flexible to provide motion also when it is windy, because otherwise you keep moving with your building even if there is a little bit of wind. So there will be an adequate restraint with respect to small deformations of the bearings. So for instance, against the wind loading.
Professor, one question, sorry.
Yeah. Yes.
What is the frequency for the test that is specified in the
document? Either it is defined by the structural engineer or it could be equal to 0.5 Hertz.
Thank you.
You're welcome. And so according to the frequency and according to the assumed maximum displacement, we can compute the maximum velocity, which is equal to 2 pi frequency maximum displacement. So this will be the key value for the velocity time series. Generally, when we have to carry out tests in a laboratory, for instance, at the Center Foundation, we have to provide all the characteristics for the test, that is the waveform, so sinusoidal, the frequency, the maximum displacement, and the velocity. And generally, we have to consider, according to the assumed waveform, we can compute the maximum velocity according to the maximum displacement and frequency, rather than in some applications, in some tests, we are provided with the maximum velocity and we have to compute the frequency. But again, we can compute the velocity with this expression rather than compute the frequency as the ratio between the maximum velocity and 2 pi, the maximum displacement. So this happens, for instance, for curved surface sliders. In the testing protocol for curved surface sliders, you will see that it is given the velocity, which is generally provided by the structural engineer. It is not a single value which is given by the standard code, but it should be defined by actually the structural engineer. So by having the maximum value of velocity, we have the maximum displacement, which is also provided by the structural engineer, and we compute the frequency according to this is obviously these are related to sinusoidal waveform. Another waveform which is used for horizontal tests is the triangular waveform, and the expressions are slightly different. Generally, the triangular waveform is used when we have very low velocities. And it is a particular waveform because, as you know, if we have a triangular waveform, so something like that, the waveform is always related to the displacement signal. If we have something like this, this means that the slope for each branch is constant, and the slope of the displacement time series is the velocity. So this means that for all the branches of this waveform, we have a constant velocity. And this is a particular, and it is a square wave, if you know. Velocity over time, it is something like this. So it is called the square wave. Okay, so it is constant within the same branch, and it is obviously different with respect to the sinusoidal waveform of displacement, which leads to a cosine as a time series of velocity. So the coefficients here varies a little bit. If we have a triangular, so 2 pi automatically becomes 4. So that is the only difference. Then up to now in that paragraph, the tests for the dependence of the mechanical properties on the shear strain are listed and discussed. In this paragraph, we have tests for the analysis of the dependence of the mechanical properties on the frequency. So before we kept the frequency constant as a constant value, and then we varied the shear strain. In these tests, we do exactly the opposite. So this means that we keep, okay, again, the vertical load constant and fixed, let's say fixed. Now we keep the maximum displacement fixed, and we vary the frequency. Okay, so you see the effect of frequency on the effective stiffness and the equivalent viscous damping for rubber bearings, rather than the post-yield stiffness and the strength for lead rubber bearings. Shall be determined by the test performed at a rubber shear strain of amplitude 100%. So you see that the maximum displacement is referred to 100% of shear strain, and you see the horizontal characteristics should be measured at 3 frequencies. So there are values recommended. Obviously here they have been deleted. I remember that there should be 0.5 hertz, 1 hertz, and 2 hertz. And you see other values spaced by the same ratios may be chosen in agreement with the structural engineer, and so on. So you see there is no more than 20% of the with respect to the middle the middle frequency, and yeah, then there are some some restrictions for the scale procedures, but nothing important. Okay, this is another test. So this is what has been called within the testing protocol frequency dependence test. Okay. Okay, and the previous ones, the dependence on the horizontal characteristics are actually HC, horizontal characteristics test. But we see the final table for the testing protocol. Then there is another important test, which was the one mentioned before, the repeated cycling. And actually, it is again for the evaluation of the mechanical properties, effective stiffness and damping ratio for the rubber bearings, rather than post-yield stiffness and strength for lead rubber bearings. Repeated cycling loading at 100% of shear strain if requested by the structural engineer, but generally this is a key reference. And these are the requirements for this particular test, which rules actually the ratio between the minimum and the maximum value of the mechanical properties measured in the cycles between the second and the 10th. And the difference shall not be less than 70% for KB or K2, 70% for the damping rather than the strength, and again for the stiffnesses values between the first and the 10th should not be less than 60%. So we have just to check the values for all the cycles, and then we know that under repeated cycling excitations we have a degradation of the mechanical properties for the bearings. We will try to see this aspect tomorrow for the real tests. And these are again for scaled other restrictions for scaled isolators, and if we need to consider more than 10 cycles, but generally for what I have observed in the experimental activity of the U Center Foundation, generally we assume in almost all cases 10 cycles. Then there is another important test, horizontal test, which is the lateral capacity test, LC, which is capacity in compression under. Okay, no, this is the compression capacity. So this is lateral capacity is the next one. Compression capacity under zero lateral displacement. So this means that this is a vertical test, and you see the isolator should be able to support a vertical load equal to NSD, which is permanent load plus a combination of non-seismic live loads. And actually, we have to apply the vertical load up to NSD by maintaining constant the value for 3 minutes, which the isolator is examined for failure, damage, and so on, and then the load is removed. So it is exactly the trapezoidal waveform. So now the input signal is not a deformation, so it is not a displacement, but it is a vertical load. And there is a ramp, then we keep it constant, and then we go back to zero load. And this time window should be at least 3 minutes. Without any kind of horizontal movement. So this is just a vertical test. we have to see if there is a sign of one failure, misaligned.
So it's a force control test in general.
This is the only difference where we use the force control. So we just apply. Okay, it is a mixed one. I explain what I mean. Generally, what happens is that there is a gap within the restraining vertical part of the equipment and the bearing. Then the operator allows the equipment to go up in displacement control. As he sees that the vertical load starts to increase, he switches from the displacement control to the force control, and then he applies this signal. So it is generally the overall test is performed in force control, as you mentioned, but after having reached the top of the testing equipment, so having achieved the initial gap between the equipment and the bearing, and then after the signal is applied. So this is only for vertical tests. Generally, the force control is used, and other issues are obviously surface cracks, imperfections, and so on. So this is just to see if the device is able to withstand the design vertical load. Just because we have to remind that these devices are just structural bearing at the beginning, and then they could be also isolation devices. And then this is what I mentioned before, the lateral capacity, the horizontal displacement capacity, where the trapezoidal waveform is used as a time series of displacement. So we reach the maximum displacement, which is generally, you see, an increased value of displacement. You see, for a partial factor for elastomeric isolators, generally is 15% more. So we slightly increase the design displacement, and then again we achieve the maximum displacement constantly with a constant velocity, so a ramp, and then we keep it constant, and then we go back to zero, rather than ramp input, you see, and then again we have to see if there is some failures, some cracks, or imperfections, and it could be performed at two different values of vertical load, which are actually representative of the variation of the vertical load with respect to the previous numerical analysis performed by the structural engineer. And finally, this is very, very fast. This is just for the compression stiffness. This is in force control, and it is a vertical test, which is just to able to provide the measurement of the secant compression stiffness. And this is the final table for the testing protocol. You see all the possible tests with all the relevant reference within the standard code, and all the peak quantities for displacements, velocity, frequency, the load shape, which means a waveform, the vertical load, and the number of cycles. Okay, you see there are compression stiffness, which is the one that we have just seen, the horizontal cyclic characteristics, which are tests, you see, defined according to a varying displacement by keeping fixed the frequency, which could be, as I mentioned, 0.5 Hertz, or the isolation frequency provided by the structural engineer. The waveform is sine. Then, yeah, one side horizontal stiffness. These are additional tests, but generally they are not performed. Frequency dependency is what I mentioned, with the fixed 100% shear strain and varying frequency. You see 0.1, 0.52, or different values of frequencies, and you see that the vertical load is defined according to a pressure 6 megapascals. So this means that the vertical load is computed according to the size, the planned sizes of the device. According to the plant size, maybe it is a circular shape with 6 megapascals, so you can compute the vertical load. Then there is the repeated cycling dependence with 0.5 hertz of frequency or isolation frequency, 100% of shear strain or design shear strain if different, sinusoidal, 10 cycles and 6 megapascals of vertical load. And then there is the lateral capacity, compression capacity, creep, which is optional, and aging. Aging is somehow able to provide evidence of the effect of aging, which is aging obviously can be produced artificially by putting the device inside of a beaker up to, I think, 70 degrees for a number of days, so that you are somehow simulating the effect of aging. So I just want you to have a look at some tests. This is an ordinary test. I don't know why it doesn't work. So this is I just show. I don't know why it doesn't work, but maybe because there is. Okay, yeah. Okay, now it works. This is an ordinary test. You see, the motion is applied at the bottom. This is the testing equipment at the Center laboratory, and we will have a look at the testing equipment later on. And then the force is recorded, which is needed to apply the displacement time series. This is actually what happens when everything works. The next video shows what happens when everything doesn't work. So this could be the failure of a rubber bearing, where the maximum shear strain is too much for the bearing, and so this is what happens. There is the failure of a layer, and maybe this is a failure between a rubber layer and a steel layer. So this bearing becomes actually a sliding bearing, but the sliding interface is a rubber over steel or rubber over rubber. So a very high value of the friction coefficient. And generally, what happens in reality is that if this particular failure occurs, then we can consider a sliding device there, but with a huge value of friction coefficient. So maybe there will be no movement anymore. But here we have movement, just because remember that these tests are performed in displacement control. So this means that regardless the force, the testing equipment applies that displacement. So this means that it goes anyway on during the test by applying exactly the same time series of displacement. Obviously, we will see the changing of the force response in the recordings after the test, and we will be able also to see what has happened during that particular time instant. Okay. I think that we are done for rubber bearings, and now we can start with the surface slider. I ask if there is some questions for rubber bearings generally.
Yes, one quick question. Is it specified that the same device has to pass all these tests? Yeah. It has to be the same. And what happened to the device after the tests are done? Is it usable in a structure, or it has to be discarded?
Yeah, no, actually, it could be directly installed in the real application if no damage occurred during the testing protocol, rather than maybe it strongly depends on the structural engineer and on the producer. Maybe it can also be just one prototype to be tested for the purpose of the checks of the standard code, and then other devices go into the real application.
Perfect, thank you.
You're welcome. Yeah, but generally all the one device, all the devices which have to be tested, which are portions of the total amount of devices which have to be installed, have to pass actually all these checks. Okay, other questions? Okay. So let's have a look at the testing protocol for curved surface slider. It is exactly similar to what we have observed for rubber bearings. Obviously, we have different tests because actually the behavior is different. And you see that there are some, again, some definitions. These subclause applies to seismic calculator that provide the 4 main functions, which are obviously all the characteristics that we have mentioned yesterday, last lecture. So the period shift, the damping, and the recentering through an appropriate arrangement of curved sliding surfaces, and the use of a characteristic of a pendulum that lengthens the natural period of the isolated structure. So the curved surfaces, which leads to the pendulum motion, also provide not only the recentering behavior to the device, but also the period shift. And so we have to remember that the not only the restoring force is provided through the spherical shape of the sliding surfaces, but also the high energy dissipation capacity is provided by the frictional response. And also there are rotations which have to be allowed because generally they could be installed within bridges rather than the buildings, and we could have also relative rotations between the top and the bottom plates. So this is the first test, which is a load-bearing capacity, and again, this is something like the compression capacity, the compressive capacity for rubber bearings. This is just to ensure that this device is a structural bearing. Remember that the isolation devices should be structural bearings at the beginning. So no lateral displacement is applied, and the device has to be subjected to twice NSD, which is the design vertical load due to the dead loads plus the combination of non-seismic live loads. And it should not be damaged. The sliding material should be with no degradation of the surface and so on. So this is just the application of vertical force, and the actually the waveform is a trapezoidal waveform. Then there are different tests for horizontal displacement capacity. Here, the maximum displacement looks like to be actually amplified, but then the maximum the coefficient is equal to 1, so it is exactly the design displacement. And the same also to ensure that the device can accommodate actually rotations. Okay, and this is one important test which allows to actually to measure the frictional resistance, which is actually the name of the test, FR, frictional resistance. And when there are very slow motions occurring, so this is frictional resistance. And this is actually the aim of this test is to measure the static friction when actually the motion is very slow. So the because generally we don't have just a single value of friction coefficient, but we can have an increase at the very beginning just because it is the bearing is stopped at zero displacement, and it starts immediately to move. and maybe we have in some applications with some particular specific sliding materials, we can have an increase in the friction coefficient, which leads to the definition of static friction rather than breakaway friction. Which breakaway means that it is measured at the beginning, at the very beginning of the motion. So generally, if we have the force displacement loop, we have something like this, and then go back, and then we have something like this. So this increase, this is due to the breakaway friction.
I'm sorry, Professor.
Yeah.
We usually have, we always have this kind of over strength, over force, let's say at the beginning, or it depends on the material that is used for the surface. I mean, for the different producers of isolators.
Yeah, generally it is exactly like that. It strongly depends on the material and on the producer. This is a very dangerous parameter because, as you may know, if this difference, the ratio between the breakaway friction and the design friction is very high, it could happen that the isolator will not move in any condition because the breakaway friction is very high. So this means that you have designed the isolation devices, but your isolation layer cannot deform because there is a very high breakaway friction. So even if your structure is an isolated one, it is exactly like having a structure with a fixed bay configuration. Okay, so this is a very important parameter to evaluate because otherwise you design, you attend. Actually, you are expecting to find a specific behavior of a base isolated building, for instance, but then it behaves exactly like a fixed base building because there is the breakaway effect. You see that? Yeah, this is just a drawing. It is not on scale, but it could be exactly like that in real application, in which the breakaway friction is of the same magnitude order of the maximum force, which is achieved at maximum displacement.
Yes. Okay, thank you. But in this case, should the producer give me the two values, or should I assume some relation to assess this difference? I mean, the producer should tell me, I don't know, about the kind of friction that I should use for, let's say, the static and the dynamic, and during the dynamic movement, or not?
Yeah, generally it should be like that. The producer should should prove that the material has a breakaway friction of a certain amount. And what happens is that you as a designer go to producer and you say, I need this typology of devices with these characteristics. So maybe you need a curved surface slider devices with this friction coefficient. And then maybe the producer says that I have a material with this breakaway. So you can decide if this material is suitable for your application rather than you have to choose another one.
Okay, thank you.
Okay, you're welcome.
Sorry.
Yes.
Sorry. So what you mean, doctor, is that this breakaway friction is a material dependent and not geometry dependent of the isolator, isn't it?
Yeah, it is material dependent. Exactly. There could be also some influence of the shapes, generally of geometry, but generally is related to material because with the given geometry, we have noticed in experimental activities that same geometry can lead to different friction coefficient behaviors, just depending on the materials, obviously. The breakaway friction can be much reduced if we consider lubricated materials, sliding materials, obviously, but at the same way you are reducing also generally the friction. So you have to check if yeah, you have to check if the your application can need actually a low friction rather than you need a given specific value of a friction coefficient. So you need just that value of friction coefficient with no breakaway. Okay, so now let's move on to the other. Okay, so now these are, yeah, you see breakaway frictional force. We have to check this. And this is actually different. Okay, I just want you to mention here this. The breakaway is different, is approximately the same effect, but it is different than the stick slip effect. If we consider the force displacement loop of a curved surface slider, we have something like this. Okay. And we have seen the breakaway is something which occurs at the beginning. Okay, so the increase in friction. The stick slip is something which occurs when we actually change direction. So we get here by increasing displacement, then we go to go backward. So we have this unloading branch, and then we can have an increasing value of friction again. But this is breakaway. And this is the stick slip. Effect. So both of them are increasing of the friction coefficient, but the breakaway occurs at the very beginning of the motion. The stick slip occurs whenever you change direction, but once the motion actually has started. Okay, so they are slightly different, but they could be modeled in different ways, but actually they are related to different aspects. So now there are yes.
both of those observations, which is the breakaway and the stick slip, they practically happen in the first cycle, where you have the initial loading and the initial unloading, right? And then they don't happen again.
I mean, the breakaway just at the beginning.
Yeah.
But the stick slip whenever you change direction. So this means that occurs here, but occurs also here. Because you go here and then you change again, and then you have something like this. And then again, maybe you have 2 or 3 cycles. Every time you change direction, you can have stick slip. Then maybe with the other cycles, with all the cycles of the test, it could be reduced as well. But it could be it could happen actually whenever you change direction.
Yeah, I understand. Thank you.
Okay, perfect. Welcome. And then we have these 3 dynamic conditions, which are actually 3 dynamic tests. And we have to check if there is no more than plus and minus 10% of changing of the restoring stiffness. For each cycle, the restoring stiffness, and this is important, of the upper portion of the cycle is within 5% of the value obtained by the lower portion. Okay, I mean, they have to be very similar. The restoring stiffness, I mean, of the upper portion. This restoring stiffness should be approximately within 5% of the one measured below. And then the average restoring stiffness of the 3 cycles, because these are 3 cycle tests, should be within plus and minus 15% of the design values. The same for the lateral force, and the energy dissipated per cycle, the EDC, you see it is defined within this standard code, should not be less than the 85% of the design EDC. And the restoring stiffness of each cycle and the average restoring stiffness of one specimen is within plus and minus 15% of the same stiffness of other specimens if we have multiple specimens for one contract. But the one important aspect is how to compute actually these restoring stiffnesses, because actually what we have is if we want to zoom to these to this portion of the force displacement loop, we have something irregular, which is actually the recorded signal, and we want to model it like a linear branch. Okay, so we will be able to compute just a linear stiffness, which is just a line, according to a least square procedure. And there should be later on in the slides the definition. And tomorrow we will have to apply this procedure in order to compute actually the average behavior for the recorded signals for the computation of the restoring stiffness for the top part and the bottom part for all the loops. Then there is service conditions, and there are all the requirements for integrity of overlay. These are just to check if there is any damage, any cracks at the sliding surfaces, seismic conditions, and bidirectional. Bidirectional should be actually a test with the bidirectional orbit, which is actually the cloverleaf, something like this. This is a path which has to be applied to the device in horizontal way. So this is a bidirectional motion, but generally what happens is that the laboratories worldwide cannot apply simultaneous components, X and Y displacement components, so the simultaneously. So this means that there is another aspect to consider for this test. The standard code actually allows all the laboratories not to consider the bidirectional motion if they are not able to apply that, but just to consider again a radial motion, so exactly a unidirectional motion, but in the orthogonal direction. So what happens is that the technicians just rotate in the plan view the isolator so that we are able to apply the same motion but in the orthogonal direction. And then we have to see if there is no sign of buckling, permanent deformation, or damage, any damage to the isolator. And then there are benchmark, verification tests, P1, P2, and P3. You will see finally all the requirements. And this is okay. This is actually what I mentioned. This is another requirement for the horizontal force, which shall be within plus and minus 5% of the average restoring force. And this is the procedure. The average restoring force shall be obtained from the best fit straight line determined by least square interpolation of the response between plus and minus 95% of the peak displacement. So this means that we have our force displacement loop, something like this. Okay, we have to consider within a plus and minus 95% of the peak displacement. So this means that we are here and we are here. And then we have to, okay, let's consider that here we have something irregular, and also here, because this is experimentally recorded. And here we have to compute the numerical best fit curve, linear curve for the computation of the average restoring force. And this is actually what we are going to do tomorrow for the tests for curved surface slider. And obviously this can be done for all the cycles. Again, this has to be done for all the cycles provided by the input signals. So if we have 3 cycles, we can compute for cycle 1, cycle 2, and cycle 3. So we have a couple of values of restoring stiffness for so the top and the bottom one for cycle 1, so 2 other values for cycle 2, and 2 other values for cycle 3. These are other requirements related to the waveform. Continuous plot for horizontal force should be recorded and provided, and the waveform is sinusoidal. The frequency shall be properly chosen in relation to the stroke, so the maximum displacement and the peak velocity. You see that in the rubber bearings, the frequency is given and you compute the velocity. Here, for curved surface slider devices, you have the opposite. You are given to the velocity and you compute the frequency according to a sinusoidal waveform. And then this is an important parameter for curved surface slider, which is the dynamic friction coefficient, which is computed according to these expressions. AHI is the area enclosed within the hysteresis loop at the ith cycle in kilojoule. And actually, it is exactly what we have called energy dissipated per cycle. So this is EDC. Okay, and you see that this is a sort of average friction coefficient per cycle. And it is computed by dividing the energy dissipated per cycle by 4 times the applied vertical load times the maximum displacement of the applied ground motion. Okay, this is when this is measured for the first cycle, and then this is when it is computed for 3 cycles. So you see that it is just a mean 1/3 of this summation. So the mean value. So why we use this expression? Well, because we have to remind that the curved surface sliders, as we have seen yesterday, if we look at the force displacement loop, we have something like this. This is vertical, and also this is vertical. Okay. Okay, this is the general force displacement behavior for curved surface slider, but we know that this is the result of the superposition of 2 behaviors. The recentering one, which is linear, and the frictional one. Okay, and we generally go to the maximum displacement. So this is minus d max, and this is d max. And the energy dissipated per cycle is the integral of the force displacement loops. So this means that it is the integral of this diagram. Okay, this is EDC. Okay, so EDC is the result of the integration of the force displacement loop, but the integral is as we generally know from mathematics, the integral is a linear operator with respect to the summation. So this means that the integral of the summation is the summation of the two individual integrals. So this means that if we consider the force response of the curved surface slider as the summation of these two contributions, we have actually the integral of this is just the summation of these two integrals. But as you see, the integral of this linear behavior, the recentering behavior, since it is linear, since there is no hysteresis, there is no area. So this means that the integral of that contribution is 0. So this means that the area of this rectangular shape is exactly equal to EDC. And this is exactly what we already know, because actually the only dissipative capacity of the device comes from the frictional behavior and not from the recentering force. But EDC now can be easily determined by looking at the hysteresis shape, which is just a rectangle. So EDC is the area of that rectangle, which is twice the max, which is the base, times the height, which is twice the applied vertical load times the friction coefficient. So if we collect the friction coefficient, we get friction coefficient equal to EDC over 4 times the max vertical load, which is this one. So this assumption comes from the superposition of the effects between the recentering behavior of the spherical shapes of the sliding surfaces and the frictional response. So the overall dissipative capacity of the device is addressed to the frictional response, and the overall frictional response is associated to a rectangular hysteresis rule. And so where this expression can be drawn. So this is the final table of tests, which is actually provided within the standard code. Where this is not the same for rubber bearings, because there is no table for rubber bearings like this. But then this is actually this is the table that I provide. We generally use this table for our testing protocols, which actually summarizes all the characteristics of the aforementioned tests. You see that there is there is a free test, which is just a vertical test. The main degree of freedom is related to the direction of the test. Vertical stands for verta stands for vertical, long stands for longitudinal, and there are D1, D2, and D3, which are the longitudinal, the dynamic ones. You see at increasing value of displacements with a given velocity, and the frequency is computed according to the velocity and the displacement values, according to sinusoidal waveform and 3 cycles with constant vertical load. Then there are seismic. Again, all of them are 3 cycles, but the service one, which is 20 cycles, but with very small displacements, which is the non-seismic, so very small. And also you see very slow, because it is 5 millimeters per second. Okay, and I just concluded this lecture by showing an overview of the bearing tester system, which is installed here at the Youth Center Laboratory in Pavia. There should be the audio here, and now it should work, because maybe there was a checkbox which I didn't click yesterday. Just let's see. This is also shared within my YouTube channel. You will see also there. I just allow you to see the main characteristics of the equipment, and then we will discuss which will be tomorrow the main signals that we will have to analyze. These are some technical details. You will see maximum displacements, velocities, vertical loads. The vertical load can achieve actually up to 50 meganewtons, so 50 meganewtons. And this is how it works. There are jacks, hydraulic jacks, which leads the isolation to this place. This is actually a special setup for bidirectional motion, like the one ruled by the standard code, the Cloverleaf orbit. And this is actually a double concave surface slider device. You see the hysteresis loops is highly nonlinear when a bidirectional motion is applied. And now I will show the experimental behavior of a double curved surface slider. I think that this video was the one shown yesterday. And this is actually the experimental outcomes that we are going to consider tomorrow. Exactly like this. We see that there is a sort of degradation of the friction coefficient as there is the application of multicyclic excitations. This is actually what we are going to measure tomorrow. And this is the recycled rubber bearing that we have seen yesterday. What I didn't mention yesterday, maybe it was that the bearing is unrestrained horizontally, so you will see also uplift of the lateral faces. So this is also a hybrid simulation. So this means that we have the interaction between the experimental facility and also numerical modeling of a building. So this is actually an earthquake simulation. So this is not a sinusoidal waveform, but it is actually the result of a time integration, which is also actually provided together with the numerical simulations and together with the experimental outcomes, which works together actually. And this is the overall data that we are going to consider tomorrow. So actually, we will consider the longitudinal displacement. FBK stands for feedback. The feedback is opposite with respect to reference, and these are generally definitions whenever we consider structural control, active control. So the reference is actually what we ask the equipment to do. The feedback is actually what the equipment does. So we want to consider the feedback because it is actually what is recorded during the test. The test is well performed, obviously, if the feedback is very close to the reference. So the equipment is actually able to provide the same input signals that we assume at the beginning. So the longitudinal displacement will be actually the relative displacement between the top and the bottom plates of the devices. The longitudinal force feedback, so the force which is applied to this sliding bench in order to apply those displacements. The applied vertical load, this is the arch, the reaction arch, which provides actually the vertical load, and the vertical displacement feedback, and obviously below there are other hydraulic jacks, which provides actually the application of vertical load and also the movement, the vertical movement. And we are expected to find approximately no vertical deformation for rubber bearings because we are expecting to have planar behavior. For friction pendulum, for curved surface sliders, we are expecting to find the actual movement, pendular moment for the bearings. So actually, we will try to understand and to measure which is the radius of curvature of the device by looking at the vertical deformation and the horizontal together with the horizontal one. So for a number of tests, we will consider these signals in order to come up with the main important parameters for those devices, and these will be actually a portion of what is generally done for both commercial and research applications in testing laboratories. So this is it for regarding the testing standard, the European one for anti-seismic devices. Is there any question about this?
Professor, I have a quick question.
Yeah.
In the rubber bearings, we saw that some of them experienced rupture and maybe cracking of the rubber. Yep. But in the friction devices, is there evidence during this test about the deterioration of the sliding surface or etc.? Is it normal?
Yeah, there could be. And actually, one of the weakest material, weakest component of those typologies of devices could be the sliding material, because the sliding material is actually something plastic, and with respect to the other portions of the device, which are actually made of steel. And I go back just to show the drawing, if there is, or maybe there is the final. I try to see. Okay, there is here. I don't want you to listen to the music. I don't know how to switch. I cannot. Just a second, because I want you to see actually. Okay, I just switched off the. Okay, can you see the video, right?
Yes. Yes.
Okay, perfect. I think. Okay, we can see some damage here, but this test, which is the hybrid simulation, so the interaction between the numerical modeling and the experimental part. This is a particular test because, as you see here, for the displacement time series, we have a dashed line, which actually represents the design displacement, so the maximum displacement which can be applied to the device. After that value of displacement, the internal slider starts to get out with respect to the sliding surface. So what happens? Try to look at the portion of the sliding material. So there are portions of the material which are actually cut, and that is a huge damage. But that is for a very severe earthquake, which is actually not a design earthquake, but an over-designed earthquake. And this is a huge damage which can occur. But what we have observed in this research is that even though the maximum displacement is overcome, the overall force response is pretty stable, and it can be modeled just as an increase of the friction coefficient. So the damage which occurred at the sliding material can be just modeled as a little increase of the friction coefficient. You see here, I just try to stop. Just look at the video of the test when it go now. Okay, you see that there are portions of the materials which are just cut and falls outside, and they fall outside the bearing. And these are actually the effects of what we call the overstroke behavior. So the stroke is the maximum capacity of displacement of the device, and as we reach the maximum displacement, you see the increase, but the limited increase in the friction, and also in the other part of the other portion of the force displacement loop. So this is the maximum damage that you can have if you don't go for if you don't go I mean for displacement further. I mean for displacements higher than that value. ordinary damage can be just very little, detachments of the sliding materials rather than some buckling effects of these sliding surfaces, because actually the sliding surface is made up of a backing plate, which is a spherical shape, and then a very thin layer of stainless steel. So maybe if the layer of stainless steel is too thin, you can have also buckling, but those are the main damage, sort of the sign of damage which can occur.
Very interesting, thank you. And one more thing, in these devices, do they have like a kind of retaining rim or something that won't allow the...
Well, I think that there was, I don't remember if there was a sentence here in this presentation, but I can assure that there is in the real in the standard code. I don't think okay, there is not. Okay, this is in the horizontal displacement capacity. There is this sentence: the isolator shall not include any mechanical elements that serve as end stops, such as containment rings, to avoid the possibility of any impact between rigid mechanical elements causing damage to the device in the event the displacements larger than the amplified displacement take place. This is actually a rule for European standard, so there must not be any containment rings for isolation device curved surface sliders in Europe. But generally, the restraining rim is actually very studied in United States. There are a number of researchers and professors which are investigating the effects of the containment rings, the restraining rings, with respect to the response of the buildings rather than of the isolation device itself. And one of them is Professor Michael Costantino of the University at Buffalo. He uses the restraining rim, especially for triple friction pendulum. But there is also Dr. Tracy Becker, which is actually studying these effects in his inner research activity. But this only happens in the United States, but not in Italy. In Europe. In Europe, is actually avoided.
Professor, sorry, so many questions. This is the last thing. So
yeah, no,
if there's no retaining mechanism, the isolator will just jump out, right?
Yeah, it could at the beginning. What I've just shown happens. So there is the increase of the friction, but then there is a limitation of displacement, which is actually what you were mentioning. Then the internal slider falls outside the bearing, and so there is the vertical collapse of the overall structural system. So there is a huge damage.
Perfect. Thank you. It's very clear now.
Yeah, you're welcome. Other issues, other curiosities? Okay, so I think we are done also for today. So let's see each other tomorrow for the numerical laboratory. Remember that tomorrow the lecture will be from 2 p.m. to 6 p.m. But I don't want to kill you with just slides, but I want you to try to train with some data. We will do it together with some computations for real data processing for full-scale devices. I just remind you to send me an email by saying that if you need actually the connection to the remote desktop because you don't have your own MATLAB software, so that you will be able to follow exactly the same computations. So have a nice day. See you tomorrow.
Thank you, Doctor.
Thank you. See you.
Bye.
Thank you. See you tomorrow.